Thanks. All right. First, any questions about the assignment so far? It's just a couple of simple readings. One is the time management lecture. I thought you should read that first to think about it, how to manage better your time. You don't want to read that one or view that one at the end of the semester when it's too late. Can everybody hear me up there, by the way? No? Okay. Is this better? Better now? Okay, good. So I was saying the time management lecture, very important. Most of you have viewed it. Most of you have turned in the assignments last night. I appreciate it. Try to get ahead of the readings. Don't save it to the last minute, obviously. Those that haven't turned it in, you will soon hear from us by email. And if you keep not turning in stuff, we will call you in and have a little awkward chat with you. It's our way to help you, not procrastinate and force yourself to cram at the end of the semester and have a crisis. So we'll try to help you prevent that. We said that this course is about problem solving, how to become more incisive, insightful, out-of-the-box kind of thinkers, problem solvers. You know, the classical example is MacGyver. We talked about then, new generation problem solver, Matt Damon on Mars. And we left off with this problem about the centrifuge. We started solving it. We said you can spin up 5 test tubes by first realizing you can spin up 2 and 3 separately, and then superpose the 2 solutions. And the 2 solutions superposed will give you a balanced solution by the principle of merging or superposition, like that. And even though it doesn't look symmetric, it is balanced. And I have a little way to illustrate that using a demo. So you've all seen, fidget spinners like that, right? But if you make it unbalanced, the fidget spinner will wobble around. Oh, it's hard to see on the camera, but it wobbles around. If it's spun, see, it just wobbles all over the place. Here's a more interesting fidget spinner. This one is composed of 3 on the outside and then separately 2 on the inside. I hope you can see that. It's a little shiny, but there's 2 on the inside, 3 on the outside. So this together is 5, and sure enough, it spins evenly without wobbling, just like the 5-hole centrifuge. Of course, here the 2 and the 3 are decoupled. So they can independently spin of each other, not just like the example with the centrifuge where they're coupled together. What coupled or uncoupled, if both are balanced, then their superposition is balanced too. So that's an interesting observation because now you can generalize that to other solutions. You can keep adding 2 and 2 and 2 and more 2s and get larger and larger solution. Now you know how to solve larger and larger centrifuges. And you can characterize a complete set of evenly spaced holes around any size centrifuge that will be balanced or not balanced. Certainly 1 and n-1 are both impossible for the same reason. And that brings in together the principle of complementarity. If a solution exists that's balanced, the complement of that, the holes replaced by tubes and the tubes replaced by holes, must be balanced also by complementation of the original solution. From the physics point of view, balancing a bunch of positive masses is equivalent to balancing a bunch of negative masses, a negative mass being a hole, equivalently, mathematically speaking. So it's good to solve problems in a general sense, in an elegant sense, and notice this solution has a lot of benefits aside from not using any trig or calculus. Last time somebody mentioned, you can use trig, and sure enough, you could. But then you'll end up with a bunch of vectors and sines and cosines and a lot of algebra and arithmetic, and you still won't know why 5 balances. You'll just know that it does. And that's not enough. You'll be correct, but you wouldn't be insightful. Right? You won't be wrong, but you won't be wise either. So noticing the fundamentals underneath what's going on, the properties of the underlying system and the generalizations of it is very, very beneficial in science and engineering, in math, and in life in general. Even in politics, in the legal system, general principles sort of supersede and preempt or are more interesting and important than specific examples, instantiations of them. Okay, so there's no equations in this solution, right? That's an advantage. You can explain the solution to somebody off the street who doesn't know calculus or algebra or sines and cosines or trig or physics even. Truth here has no place to hide in this solution. It's pretty obvious that it would work. It's not an hypothesis. It's a slam dunk observation that must be true, right? And you expose the fundamental principles of symmetry, superposition, the linearity, the complementarity, and then allow you to solve lots and lots of other problems. So this is kind of problem solving at its best, going after problems in this fashion, right? And you can generalize it easily, and it's kind of elegant and beautiful, and you can empirically test it like we did with the fidget spinner. Actually, first tested it back in the 90s empirically before fidget spinners even existed. I went to a biologist friend of mine in the life sciences building, and I said, you know, here's an interesting problem. Can you spin 5 centrifuges? He said, no, there's no way to do it. It's not symmetric. It won't work. It'll be out of whack. It'll be out of balance. And I said, I think you can do it. And he said, no, absolutely not. Then I showed him this solution. He said, I don't believe it. It doesn't look symmetric. This configuration right here is 2 and 2 and 1. It's kind of off-kilter looking. And I said, what would convince you? And he said, all right, let's step into my lab. We had many centrifuges running. Right? He's been running centrifuges for 20 or 30 years. He had one of his postdocs fill 5 test tubes very carefully with the same amount of water, equal size, equal mass. He had him put them in this configuration, and he thought it would wobble. So he said, be very, very careful. Just spin it up very slowly because you don't want to damage the centrifuge. A centrifuge spins at about 60,000 RPM. That's about 1,000 revolutions per second. The centrifugal forces are so high, even steel will deform. So there's only one substance that can be made of to withstand these centrifugal forces. What is it? Steel is too weak. What is it made of? Say it loud. Titanium. Stronger than steel, also lighter, but a lot more expensive. That's why these things cost a bundle. So he had him spin it up and didn't wobble. So he said, okay, now go a little faster. Nothing wobbles, equally balanced, evenly balanced. They said, okay, go to full speed, and it was perfectly balanced at maximum speed. And he said, now I believe it. So this is like theory versus practice. Of course, it's nice when the practice confirms the theory and vice versa. Any questions about this problem and sort of the approach we use to solve it elegantly, generally, in a way that exposes the basic principles? Any more thoughts on this? Because that's how you should approach problems in general, when possible. I'm not saying every single possible in the world is easy to solve this way in an elegant, beautiful, insightful fashion, but sometimes you have to grind it out. But when you can, please do. Don't leave beauty and elegance on the table if you don't have to when you solve problems. Let's look at other examples of this ethos of solving problems elegantly and beautifully and incisively and insightfully. So we're not going to use induction. In fact, in this course, we will never use induction if we can help it, and it's pretty much never in this course. Now, how many have used induction before? Now, I'm not saying it's useless. So bear in mind, I'm not saying it should never be used. I'm not saying it has no function and it has no purpose. I'm not saying any of those things. I'm just saying it should be avoided if possible. And we'll talk more a little bit about induction in a minute specifically. But let's look at the problem of adding up the integers from 1 to 100. And this is the problem where Carl Friedrich Gauss, when he was 7 years old in kindergarten, he was the so-called prince of mathematics in the 1700s, one of the most prolific mathematicians who ever lived. The kindergarten teacher tried to keep the kids busy for about an hour, so they figured, okay, we'll have them add up the numbers from 1 to 100. That's good to keep a bunch of 7-year-olds busy for a while. Little 7-year-old Gauss came back in about 3 minutes and gave the answer. The answer was 5,050, and the teacher could not believe that this little kid would get the answer so quickly. And the question was, how did he do it? And there's lots of ways to do it. One way is to write it backwards underneath the original forward sequence, and then add up the columns. So this column here adds up to 101. And this column here adds up to 101 also. And each column adds up to 101. And when you add up all these 101s, how many of them do you get? You have 100 of them, right? And what's the total number of 100 times 101? Not a trick question. How do you multiply by 100? Add two zeros. So you add two zeros to 101, what do you get? 10,100. But that's not quite the answer. What is the real answer? Half of that. So it's 50-50, 5,050. And of course, this generalizes to arbitrary n, not just n equal to 100, right? And that's a much more insightful way of adding up the numbers, because if you use induction, you'll just get the answer, but you have to know the formula first. That's one drawback. And then when you see the answer, you want to understand why it's that answer. Let's solve it another way. This staircase, the area of this red staircase is 1 unit plus 2 units plus 3, that's a 1 by 3, that's a 1 by 4. Each stair is a 1 by n. So the total area of this staircase is exactly this quantity, 1 plus 2 plus 3 plus 4 plus 5 square units in total. How many get that? Okay. So adding up these numbers is equivalent to finding out the area of this staircase in red. And you might wonder, well, what's this area? It's kind of a jagged, kind of off-kilter, triangular kind of region, but not quite a triangle. Well, it's not easy to see what the answer is just by staring at that, but if you make a copy of that, right, identical copy, and then you paint it blue, right, and then you tilt it over, together they make a rectangle. And what's the size of this rectangle? The height is still n, and the width is n plus 1, because of this extra blue thing at the end. So the total size area of this rectangle is n times n plus 1 divided by 2. Okay, and that's a general formula. You want to see it again in slow motion? So beautiful. I'm really proud of my PowerPoint slides. I spend long weekends creating them. I hope you appreciate that. Try to do that yourself sometime. You'll see it's not easy. But this example gives you not just the formula. It tells you why the formula has this form that it does. It tells you a lot more information than just the answer 50-50, or generally n times n plus 1 over 2. It tells you that the formula has to be quadratic, not cubic, not linear, not n log n, not n square root of n, not n cubed, not any other thing, because it's an area. And the area is proportional to some function of n that's linear times another function of n that's linear. And so the total area must be quadratic. So it tells you there's a quadratic formula, not any other power, not any other polynomial degree other than 2. It tells you also that it's n times n plus 1 simply from this picture. It's not n plus 2 times n minus 7 or some other thing that's also quadratic. It has to be specifically these two quantities multiplied together. And it tells you also that the denominator is not 7, it's not pi, it's not e, it's not 10, and it's not 1.5. It has to be 2, because there's 2 copies of this region, not pi copies or e copies or 7 or 10 copies. So from this picture, the formula falls right out. And not only that, it tells you why the formula must look like this and like nothing else. How many get that? Okay, so this is a very insightful way to arrive at such a formula for a sum of integers. Okay. Not only that, you can explain this to anybody off the street. They don't need to know algebra or trig or calculus or even a lot of arithmetic. They just need to understand that a staircase flipped over, put over another staircase, will complete that staircase into a rectangle. That's not hard to see, even with no math knowledge. Not only that, if 20 years from now, when you're sitting at a bar having some discussion at some cocktail party, and somebody says, quick, what's the sum of integers? You will probably remember this picture. If I didn't show you this picture, you will not remember this formula in 20 years if you don't do any combinatorics between now and then. Because it's very vivid, it's very visual, it's very visceral, it's very obvious. Truth has nowhere to hide. But that problem, that is the formula. And from the picture, you will be able to infer the formula in 20 years, even if you don't remember the formula. You remember the staircase, and you say, staircase flipped over another staircase, and okay. So it's like n squared, maybe off by 1, and the denominator has to be 2, because there's 2 of them. Okay. Any questions, thoughts about any of this? It's very important principles in problem solving. And the book, How to Solve It by Polya, which is required reading, how many have started reading that one yet? How to Solve It. Good for you. There's a few that have. It's a required reading. Read that one in the next couple of weeks. It's a required reading anyway. Don't save it out to the end of the semester. Because it has this kind of arguments and insights and wisdom about lots of problems, how to approach problem solving in general in a methodical, systematic, insightful, MacGyverish way. Okay? Any other questions or thoughts about this before we move on? Okay. So what I'm telling you is that there's ways to solve problems and there's ways to solve problems. And they're not all created equal. Right? There's brute force, hackish ways that just tell you the answer and you walk away in victory as if you won the lottery. That's not enough. Getting the right answer is no longer enough. Having the right answer, don't get me wrong, is a nice thing. You know, it's much better than being wrong about the answer, having a wrong answer. But being insightful on top of being right, and being wise on top of being right, and being generalizable on top of being right, that's even better. Okay? It gives you more tools in your toolbox as a problem solver, and as a thinker, as a researcher, as a scientist that you are. You are computer scientists. Which word is more important in this phrase, computer or scientist? Take a wild guess. How many say computer is the most important? How many say scientist is, yeah, that's the more fundamental thing. We are scientists that apply our scientific prowess specifically to computers, but we could apply it to other things as well. Okay, more about induction. So in induction, you must know the formula before you start. And in this picture I showed you on the previous slide, you didn't have to know the formula at all. The formula fell out, came right out of the picture. Using induction, you have to know the formula, and that's a drawback. What if you don't know the formula? Induction won't help you. Induction basically shows you how to verify a formula once you're given that formula on a silver platter. But if nobody hands it to you, you have no idea what it is, and induction won't help you. It's easy to make mistakes in induction. If you do this using induction, there'll be a full page of algebraic manipulations with lots of equations and collection of terms and so on, and squaring things. Easy to make mistakes, and easy to write down correctly, and easy also hard to grade. Even when it's correct, it's hard to look at it and say, yeah, you're right, without checking each and every tedious step. Right? It's very mechanical. It's not intuitive. You're just going through the motions when you do induction. You know, it's like cutting and pasting answers from the web onto an exam and thinking you aced it. No, you didn't, and not only that, you cheated. But induction is very mechanical. It doesn't shed light on truth. It's tedious to construct, hard to check, hard to grade, hard to understand. You can't convince somebody on the street that some inductive proof is correct. They won't even understand what you're talking about when you say induction and start arguing inductively. But with a picture, they will get it right away. Right? Induction is not generalizable. If you want to prove some other thing or some other form, you just start from scratch. You can't take an inductive proof, tweak it a little bit, and get another inductive proof. You got to start grinding it out from scratch on a new proof. Worse, it doesn't shed light on truth. It doesn't make you any wiser or insightful or generalizable or a better problem solver. It just gives you a crank to grind and grind and grind until it cries uncle, and then you walk away thinking you won something, but you didn't. And it obfuscates connections to other problems and generalizations to other things. Right? So what I'm telling you is if you have a problem that you're trying to get rid of, some nuisance, some issue that you're trying to nail, don't do this. Okay? I'm not saying, you know, a shotgun or a minigun will not kill a fly. It will kill a fly. But it will do worse than that. There'll be a lot of collateral damage beside the fly being gone. And one of the collateral damage of using induction, your intuition will suffer. Your insights will be hobbled. Right? Your generalizations will not be there. And you will not be any smarter or a better problem solver. So only use induction as a last resort. By that I mean rarely. I don't mean never. You know, occasionally there's a problem where only induction works and nothing else works. That's very, very rare. And in this course, I don't even know that we'll see cases like that. Although we could run the course, half the course, we can run it on induction if we so chose. But I won't do that to you. And if I did, I would be doing you a disservice. Okay? So induction, just say no. Okay, now again, in some years ago, I said the same thing to a bunch of students, and then they went around saying, oh, Professor Robbins told us the induction doesn't work and it's bad and you should never use it and it's terrible. I didn't say any of those things. I didn't say it's terrible. I didn't say you should never use it. I didn't say it's bad. What I'm saying is induction is like overkill that shouldn't be pulled out of their arsenal as a first resort. Induction is like a nuclear weapon. You don't pull it out the first time somebody pisses you off. Now, a nuclear weapon may have its uses very, very rarely in extreme conditions, almost never, and then you may be glad you have one in your arsenal. But until then, try every other possible way of doing it without resorting to a nuke. So that's what I'm talking about when I say avoid induction if you can. Okay. I'm not saying never. I'm not saying it's terrible. I'm not saying it's wrong. I'm not saying you should, not use it under any circumstance. Okay. How many get all this? Okay. Any questions about that? Issues, comments? So don't go around saying Professor Robbins said induction is wrong. It's not wrong. Yeah, question? All right. So let's look at another problem. Sum of powers of a quarter. A quarter plus a quarter squared plus a quarter cubed plus a quarter to the fourth. What is that equal to? Anybody know? So basically we're talking about the infinite sum over 1 over 4 to the I for all I. And we're looking for some geometric-based, picture-based proof. Just like the staircase for the sum of integers, try to come up with a similar looking, using colors and geometric pictures, proof for what the answer is here. By the way, what is the answer here? Anybody know? 1? No, it's not 1, but it's a good try. Okay. 1/2? 1/3? Anybody else? So we have 1, 1/2, 1/3. So we have 3 different answers so far. And they can't all be right because the answer is a unique number. Right? It's not obvious what it is. Now, I'm not asking you to look up a formula for this. I'm asking you to come up with a proof. And the proof should be picture-based, just like the staircase for the previous slide. So something that you look at and you say, okay, yes, perfectly clear. It's obvious why the answer is X. Okay, so generalize it. Any thoughts about how to do that? We're about to do that. By the way, if you have the answer, claim extra credit, submit it to the website even as we speak. All right, so what is the sum? Well, here's a quarter. Here's a quarter of a quarter. Here's a quarter of a quarter of a quarter. So the sum of all the red areas is this sum up here. How many get that? Okay, because it's a 1 by 1 square. Right? So this infinite sum is what we're after. And it goes on forever all the way down to 0, 0 here, whatever. And it's not clear what that sum is. But if you put another sum just like it, a quarter and a quarter of a quarter and a quarter of a quarter, so the blue is equal to the red. How many see that? Just did it that way. Now what's the blank areas here? That's a quarter and a quarter of a quarter and a quarter of a quarter of a quarter and so on. So we have this sum here. How many times in the square? 3. So what's the answer? 1/3. Now it's obvious. We don't have to wonder if it's a half or 1 or a quarter. It's a third. And it has to be a third. It has no choice. There's nowhere for this truth to hide here that the answer is a third. Okay? And that's very insightful. And you can generalize that to other things. Right? Now, the person that said a third at the beginning, how did you know it was a third? You're right, but how did you know? Okay, sure. Yeah, take that as S, multiply it, subtract it, come up with, and then you'll have it, but that's a lot of algebra. And you can also do it using some general formula. There's a general formula for, exponential series, right? There's an exponential series, and how many know there's an exponential series formula for arbitrary, base and an exponent goes on forever, and you're adding up all the terms. Okay, well, if you didn't know it, there is, and you can deploy that too. But this is an alternate, clear, obvious way to do it, and a person on the street will understand this, not knowing any algebra. A person on the street will not know the exponential form of, infinite series involving exponentials all added up. And if, even if you say what the formula is, you have to prove that the formula is correct before you can use it and so on. It's a lot of ifs and, burden of what to do. Okay? Any questions about this? So again, in this course, we'll try to look for elegant ways of proving things, of establishing truths, succinct ways that leave no place for truth to hide. Ways that are not complex and convoluted and hard to write and hard to grade and hard to understand and hard to explain, like induction. No. Now, I'm not saying that every problem has a beautiful solution like this. No, that's not true either. But when it does, don't miss out on that. Think towards that. Have a lot of tools in your toolbox that points you in that direction, and reading that book, How to Solve It by Polya, will be a great asset to you in that way. That's why I'm having you read that book as required reading. It's not accidentally, it's not just busy work. It'll make you much more MacGyverish for the rest of your life. And you'll impress people, and you'll impress potential employers, you'll get higher salaries, more promotion and advancements. People will look up to you when you can come up with stuff like that, and they can't, because they didn't think systematically, and you do, okay? So let's generalize it. We said it's generalizable. So what about an eighth, powers of an eighth? An eighth plus an eighth squared plus an eighth cubed plus an eighth to the 4. What is the answer there? Anybody care to take a guess? Now that you've kind of getting the hang of this, proof by picture, not an exponential formula, although you could do, and you can also multiply it by 8 and so on, but let's not do that. Let's have some other explanation. 1/7. Yeah, 1/7. How many agree it's a 7? Yeah, look at that. Most of the class now. How do you know it's a 7?
You could follow what we did previously, where you pretty much was 1/3 when the starting value was 1/4, so you could subtract 1, which would give you 1/7. Or you could just follow the formula, which is zero.
Yeah. So you basically generalize that to 3D. So 1/8 is this yellow volume. It's 1/8 of the 1 by 1 by 1 cube. And that's an eighth of an eighth. It's an eighth of that remaining eighth. And so all the yellow volumes, an eighth plus an eighth times an eighth, and an eighth times an eighth times an eighth, and so on. All the yellow volumes together is the series. How many see that? And together, how many of these sequences are we putting in blue and purple and green and pink and blue? How many of those sequences are going on here? 7. And together, they completely fill up the 1 by 1 by 1 cube, which is volume 1. And the 7 of them, they're all identical, so the answer is the 7th, and most of you have kind of jumped on that right away. Now, if we proved this by induction earlier, there's no way you can generalize it to the 3D case. You have to start over, and 2 pages of tedious algebra, and lots of places to make mistakes, and even if you do all this, all you'll know is that this is true. You won't know how to generalize it to anything else, and you won't be any more insightful for it. Any questions about that? And by the way, there's furniture that look like this, geometric progression, dressers that have geometrically increasing size bins, and like your jewelry here and your socks here and so on. Makes a very nice geometric progression dresser for your loved ones, if your loved ones are into math and beautiful proofs and geometric series. I don't know if it's an IKEA piece or what, but it's a nice one. Any questions about any of this so far? Yeah. Oh, okay. How many octants are there? So this is 1 octant. It's 1/8 of the cube, right? So it's a half by a half by a half. The cube is a 1 by 1 by 1. So there's 8 of these total yellow cubes around the whole cube, right? We've used up 1 of them, and then the rest falls into a single remaining one, right? Same for the purple, same for the blue, same for the green. Well, they all fall into this remaining one, right? And they start out by occupying 1 octant to begin with. There's 8 octants. 1 of them is being used for the rest of the series. All the other 7 are being used for the first term of all 7. So there's 7 of them. And it's completely symmetric. Okay. It's a good question. He was asking, how do we know there's exactly 7 and not 13 and not 2.5 or whatever? Okay, but you kind of think about it and say, yeah, it works. Any other thoughts or questions here? Yeah.
Isn't it better for you to be dividing so that it's already divided into 8 pieces, and then you choose the 8 pieces? You just leave the center piece to divide again, so that it's automatically 7 pieces each?
Yeah, you could use other pictures partitioned in other ways. Yeah, I just showed you one, but you can do others. But so, for example, what if we generalize it to 4D? What will this thing look like in 4D? A little confusing, but you can sort of see where it's going, from 2D. in 2D it was power of a quarter, right? It'll be power of an eighth in 3D, and in 4D it will be power of 16. And you'd have a tesseract, a 1 by 1 by 1 by 1 hypercube, four-dimensional cube. How many of these little cuboids, like the yellow ones, will be in a tesseract? There were 4 in the square, 8 in the cube. What do you think the answer will be in the hypercube? 16. So the sum of powers of 16, what do you guess would it be? 115. End of story. You see how it's generalized. Even the dimensions are higher where it's harder to generalize and visualize, and the patterns are there. And yeah, of course, you can use induction to prove all of these things. But you just won't be as insightful and smart and wise and generalizable and MacGyverish if you just use brute force, rote mechanical induction. Okay, there's other furniture that look like fractal-like furniture, but I digress. All right. Now, I'll give you a few other problems in quick succession for extra credit, and we'll put those on the back burner, and over the next couple of weeks, if you can solve any of them, just submit it to the class website for extra credit, for fun and profit, and get more MacGyverish over solving these problems. But powers of sum of cubes, what is that equal to? I won't tell you right now. Again, that's for extra credit offline. Powers, third powers of integers added up. Okay. Sum of cubes. Another problem is prove that the square root of 2 is not rational. What is a rational number, by the way? Most of you have seen that. Let's just say it. Yeah, it can be written as m over n. It can be written as a ratio of 2 integers, 2 whole numbers. Now, for a while, the Greeks thought that every number is rational, and then they discovered that the square root of 2 is not rational. And that was a big revelation to them, and they were already able to prove that. So it's just a few sentences of proof. It's one paragraph proof. But try to prove it yourself. Any questions about that? Prove the square root of 2 is not a rational number. It cannot be represented as a over b or m over n, where m and n are integers. Cannot be done. Impossible task. Prove that there's an infinity of primes. Prove that there's no highest prime number. For every number that you claim is the highest prime, there are primes that are higher than that. By the way, what is a prime number? Let's not take that for granted. What is a prime number?
It's a number with the only factor.
Yeah, number that can only be divided by itself and 1. It only has 2 factors, itself and 1, and no other factors that divide evenly into that number. Prove that there's an infinite number of them, not a finite number. All right. Similarly, try to prove that whether it's true or false, there's arbitrarily long blocks of consecutive non-primes. Non-prime is composite. That doesn't fly in the face of the last one. They're both not inconsistent with each other. There could still be an infinite number of primes, but could be larger and larger and larger of consecutive blocks of non-primes too. How many see that the 2 could live together? They're not contradictory. Okay. But I'm not telling you which is which here. Tell you what, it is true. Okay, I just told you the answer, but I didn't tell you the proof. So try to prove that there are larger and larger consecutive, arbitrarily large consecutive blocks of non-primes. That is a true statement. Again, very short, a few lines of proof, one paragraph, extra credit. Okay, complex numbers. Some sets of numbers are closed under certain operations. So the integers are closed under addition, which means if you take an integer and add it to another integer, the result will be also an integer. It's not trivial because some operations don't remain the set closed under that operation. So for example, the integers with respect to division, is that closed? No. Because why? Why aren't the integers closed under division? 5 divided by 3 is not an integer, and there's many other examples. Are the integers closed under multiplication? Yes. Are the real numbers closed under multiplication? Yes. Are the real numbers closed under division? How many say yes? How many say no? Ooh, split vote. Glad I asked. Take 5 seconds, think about it. Are the real numbers closed under division? How many say yes? How many say no? Okay, now we have a strong vote on the no side. Why not? Yeah, division by zero is undefined. It's a problematic. Right? One comedian said once, black holes were God divided by zero. But other than that zero, are the real numbers excluding zero? Take the real numbers, subtract the zero out of the set. Is that set, the real numbers without the zero, is that closed under division? How many say yes? How many say no? No, don't be shy. It's just a vote. Anybody want to argue one way or the other? Yeah, every non-zero has a multiplicative inverse. So the real numbers are closed under, the real numbers without the zero are closed under division. Okay, now you're getting what it means for a set to be closed under an operation. And we'll talk a lot more about the closure properties for much more complicated sets than reals and integers. Here's this problem here. Are the complex numbers closed under exponentiation? Let me ask you a simpler question. Are the complex numbers closed under multiplication? Okay, let me ask you a simpler question first. What is a complex number? I don't want to be presumptuous here. Includes I, but can include other stuff than reals and just I? It's not a trick question. I'm just asking for a definition at this point. What is the definition of a complex number?
Includes the same complex conjugate where A plus
A plus bi, and I is, just for the record, what is I here? Square root of minus 1, the imaginary quantity I. So if you have a complex number A plus bi, for arbitrary A and B being real numbers, for A and for B, independently of each other, are the complex numbers closed under multiplication? How many say yes? How many say no? What am I asking when I say closed under multiplication? What does that mean if it were closed? Complex number times a complex number would yield another complex number. Well, what else could it yield other than a complex number? Well, it could potentially yield other things. It can yield something that's not complex. Maybe it could yield a vector, I don't know, a matrix, a shoe, a bicycle. Those are not complex numbers. Okay? Obviously, it's not going to yield a shoe or a bicycle, but I'm just saying that to make the point that it's not necessarily yielding a particular thing. It could be yielding other things. In some cases, you'll be surprised what the answer is. Yeah. A could be 0, B could be 0, yeah, in A plus bi. So now that you've had 20 seconds to think about it, are the complex numbers closed under multiplication? How many say yes? How many say no? Still a split vote. Interesting. So if it's not, let's say, if it's not closed under multiplication, what would prove that? How would you prove it if it wasn't closed under multiplication? Counterexample, right? What do you say? Okay, multiply something by its complex conjugate, and the answer would be a real number. So let's be more specific now about types. Is 5 a complex number? How many say yes? Okay. So do you want to change your answer? Okay. So when we say complex number, we don't mean that the b is equal to 0 in A plus bi. If it was 0, if the b was 0, it would be a pure real number. But a real number is still a complex number. The complex numbers are a superset of the reals. The reals, conversely, are a subset of the complex numbers. The reals are all the complex numbers where b is equal to 0. So bi is equal to 0, so that complex term, imaginary term, drops out. Okay, so it was a slight misunderstanding about the definition, which brings up the point that I made last time, is be very, very precise about your definitions. So when you look at a problem, even when you have a conversation with another person, be sure you understand what they mean when they use words. I mean, this is not rocket science here. This is just common sense. Understand the definition. You need to understand what the words mean before you can reason about the words. You'd be amazed how many people just go headlong into some argument without even understanding the words that they're using. How many have seen that happen in your friends and family? Okay. In religious circles, in political circles. Don't get me started. Okay, so nail down the definitions before you start chasing them as if you knew what they mean. And then you'll be better off. Okay? You'll be more correct, more insightful, more generalizable, and you won't get into silly arguments with people as often. All right. So having said all that, so now you all agree that the complex numbers are closed under multiplication. Well, that was the easy part. The hard part is explaining if they're closed under exponentiation, the complex numbers. Let's take a quick poll. How many say the complex numbers are closed under exponentiation? How many say they're not? Split vote. So again, I'm glad I'm asking that because the answer is either one or the other. It can't be both. And if they are closed under exponentiation, what would be the value of I to the I, for example? That's one of those cases where complex number raised to a complex number gives you something. Is that something always complex? Extra credit, figure this out. Okay. And any questions about this particular problem? Yeah. Excellent question. I'm glad somebody. How is exponentiation even defined for complex numbers? That's a good question. You tell me as part of your answer how it's first defined, and under the definition, whether it's closed or not. But now you're getting it. Insist on understanding the definitions. Don't just rush in some direction as if it's obvious or as if you know it when you don't. Ask, what does every word mean in a question or a sentence or a statement that somebody makes? Excellent question. I should give you extra credit just for asking that question. Excellent. Now you're getting it. All right. You're welcome. Just submit it to the extra credit. I want to encourage you to participate, and be active and proactive and say stuff and don't just sit there and be afraid to speak up. It's okay to be wrong. It's much better to be wrong than to be silent, actually. Because if you say something, you have something to work against, something to learn from, something to fix, something to correct, whatever. Okay, anything else here? So, how about, does exponentiation preserve irrationality? In other words, are the two irrational numbers, x and y, such that x to the y is rational? So if you have a set of irrational numbers, when you exponentiate two things, is the answer always irrational? Could you all of a sudden get something rational or even an integer by some strange fluke? The converse question is easier. Are the rational numbers closed under exponentiation? How many say yes? How many say no? Split vote. And that's the easy question. Good. We're making progress. Whenever there's a split vote, the reason it's so nice when there's a split vote means half of you will learn something in the next 30 seconds. Right? Either the ones that said yes or the ones that said no, because the answer is not both. It's either or. Yeah. 2 raised to the 1/2. Two rational numbers. 2 1/2. 2 raised to the 1/2 is equal to what? 2 to the 1/2 is equal to square root of 2. Square root of 2 is not rational, right? So she gave a counterexample, and she's right. So the irrational numbers are not closed under exponentiation. And there's many other examples. Like, 5 to the 1/3, that's the cube root of 5. That's not rational either, and so on. Give me another example where not only it's not rational, it's not even real. That's even worse. Yeah, -1 to the 1/2. What is -1 to the 1/2? They're both rationals. What is the answer there? -1 to the 1/2 power. It's I. I is not just not rational, it's not even real. If something's not real, it can't be rational. Because the rationals are inside the reals as a subset. Right? The reals contain the rationals. So it's even worse than that. Okay, just saying. But again, try to come up with succinct, interesting, beautiful, short, convincing proofs. Let's not use complex analysis or quantum mechanics or some strange, heavy machinery to prove these things. It's not necessary. And whatever you do, don't use induction. Okay. All right. Here's one equation and one unknown. X to the x to the x to the x to the x forever is equal to 2. One equation, one unknown. What could be simpler than that, right? Solve for x. How many have seen this or such an equation before? There's a few of you. Okay, that's good, because it's unusual. It's unusual to see this kind of equation. But it has an answer, and the answer is unique. And I'm asking you what the answer is. Again, try to come up with some succinct, interesting, definite. Can everybody still hear me up there? I think there's some echo here, or some strange property of the microphone, but that's another problem here. Okay. Again, these are all extra credit. Work on them for the next couple of weeks. You know, turn them into the class website. If you get answers, it'll be credited. You can, you know, brainstorm over them in groups. But whatever you do, don't just look them up on the web and submit an answer that you saw on the web. That's not learning, and that's actually cheating. So, and we know where all these things are. We've been teaching it for years. We know, you know, we know a web search when we see it. Trust us on that. The TAs showed you examples last time. All right, another problem. You have a bunch of resistors connected in parallel series, kind of almost like a ladder. So this is a resistance. Let's call it R. They're all equal resistances, like, you know, electrical engineering resistance, electrical resistance, right? How many know what resistance means, electrical engineering-wise? You know, okay. So all these are resistance R, right? And the question is, and it goes on forever. The question is, what is the resistance between this point X and this point Y? If you put an ohm meter there, you can actually do this experiment with longer and longer ladders, and you'll see that it converges on some specific value if they're all R. So try to compute that. How many understand this problem? Okay, any questions about this? Again, you know, try to do it using some insight. Okay, now at this point, I'm going to skip ahead a little bit in the slides, you know, and before we talk about Aristotle and Plato and all these guys, I'm going to skip to Georg Cantor. And the reason I'm doing that for you is because in the first homework, there are questions about infinite sets and infinite cardinalities in the homework that's due in a couple of weeks. And I want to give you some background on it first so you can start on the homework early rather than wait a week or a week and a half before we finally get to it in the progression of time of the history timeline that we'll talk about. So Georg Cantor generalized set theory to infinite sets and made a lot of interesting observations about infinite sets. And he lived in the mid to late 1800s, early 1900s. And he basically the founder of modern set theory, and he invented the principle of diagonalization and one-to-one correspondence, which we'll describe now. And these two principles we'll be using over and over and over again, many, many times over. You're going to get a lot of mileage out of the method of diagonalization in this course, dozens of times. And we'll get a lot of mileage out of the method of one-to-one correspondence. And we're about to illustrate those. And he showed that there's an infinite number of infinite hierarchies, that infinity is not all infinities are created equal, is basically what he showed, among many other things. He showed that there are smaller and larger infinities. There are infinities that are even greater than other infinities, and they're all infinite. Before that, the human species had no idea that this is true. We always thought that infinite is infinite is infinite, they're all the same, and there's only one of them really, it's just infinitely large, and there's nothing more to say. He showed no, there's a whole science and theory and arithmetic behind it, and there's different infinities of different magnitudes. Some are provably bigger than others. How many of you have ever heard of that? Okay, good. We're going to use those principles again and again in this course in many contexts. That's why I put it on the first homework. That's why we're discussing it now, because it's the foundation of a lot of other results. So if you don't wrap your mind very tightly around these principles, you won't understand many other things. So pay close attention to this. And he formulated all sorts of interesting hypotheses about infinities, and he gets a lot of credit for this. And during his lifetime, infinity was considered somehow some divine concept that you should not reason about, because it would be almost blasphemous and heresy to talk about infinite as if it was a mathematical quantity. So he got a lot of flack during his lifetime in resistance, and he didn't get published very well because his peers shunned these arguments and thought they were nonsense. They weren't. They were brilliant. And much of modern computer science theory is based on these principles, including all of Turing's work, by the way. One of the people that didn't underestimate these ideas and saw the brilliance of them was David Hilbert, and he helped popularize Cantor's ideas. But Cantor, towards the end of his life, got depressed, ended up in an insane asylum, and was very sad that his work was not appreciated. And now, of course, there's dozens and dozens of books on it, hundreds of books on it, entire courses on it. Many other fields are based on these principles, and we'll see a lot of examples of that. Please read the book Infinity and the Mind by Rucker. It's this one here. It's required reading. It's easy to read. It's just a paperback. It's short. It's not very mathematical in terms of depth and formulas, but very, very insightful about the concepts, including diagonalization and one-to-one correspondences, which we're about to describe. Okay, so in terms of the book, these concepts are discussed around page 176. It's a little bit ahead in the book, but we're going to discuss them now because they don't depend on previous things and they're used all over the place. And homework number 1 has questions that pertain to that too, so that will help you solve the questions in the new homework. So we'll start by asking the following interesting question. We have an infinite hotel. By infinite hotel, we mean room number 1, 2, 3, 4, 5, 100, 1,000, a Googleplex, and on, all the way out. So there's an infinite number of rooms labeled with integers, beginning with 1. And all the rooms are full. They're all occupied with guests. So business is good, the hotel business. But you have some guy coming in the lobby, a new guest wanting a room. All these rooms are occupied. Right? So where do you put the new guest? You're the hotel manager. What do? You can tell the guest to go away, but that's not good for business. It's impolite. Up there, what do you say?
You put the new guest in the first room, put whoever was in the first room in the second room.
Good. So you take the guest from the first room, put him in the second moves to the third moves to the fourth, and so on. And that frees up the first room, and the new guest goes into the first room because now it's unoccupied, right? How many get this solution? All right. Now, you can't do this with finite hotels, right? If you have, like the MGM in Vegas, that's what, 6,000 rooms or so. You can't, if they're all full, that's it. You can't pull this trick with finite hotels. But with infinite hotels, you can. This is an example of an illustration where you can put a set, infinite set, into one-to-one correspondence with a proper subset of itself. How many understand that last statement? You cannot do this with finite sets. In fact, that's a working definition of infinity. A set is infinite if and only if it can be put into one-to-one correspondence with a proper subset of itself. Proper subset means something that's included in a set, but not the whole set. Some are missing. That's what proper means in proper subset. The subset, but not equal to the set. All right, next question. We're going to up the ante. Not one new guest comes in, but an infinite number of guests come in. New guest 1, new guest 2, new guest 3, they all come in, they all want rooms. What do? How do you accommodate them? Yeah, move every guest to twice their room number. So 1 goes into 2, 2 goes into 4, 3 goes into 6, 4 goes into 8, and so on. That frees up all the odd rooms. And all these guests go now into all the odd rooms. The first guest goes into room number 1, the second goes into room number 3, the third goes into room number 5, and so on. So in terms of a function, you doubled up all the room numbers of the guests, and that's where the new room destinations are. How many get this solution? Okay, again, you can't do this with finite sets. How many have seen this one before? All right. Let's up the ante then again. Now there's an infinite number of infinite guests. There's an infinite number of lines. Each one has an infinite number of guests in that line. How many have seen this one before? Okay, fewer of you. And I knew that. That's why I'm upping the ante here. How do you accommodate all these new guests, an infinity of infinities, into the same hotel room, such that everybody has a room? Nobody has to double up or bunk up with another guest. Every guest has a unique room. By the way, let me ask you another question on the previous one. In this solution, why couldn't you repeat this solution a bunch of times? Why couldn't you move everybody one down, then the first guest goes into the first room, and then move everybody one down again, and the second guest goes into the first room. Move everybody one down again, and the third guest goes into the first room again and again and again. Why isn't that a solution? Up there, yeah. It'll take an infinite number of steps. Worse than that, not only will it take an infinite number of steps, at the end, if you're the first guest in the first room at the beginning, what will be your room number at the end? Would it be room number 2 that you'll end up in? How many say yeah? Would it be room number 5 that you'll end up in? Room number at Google that you'll end up in? Which room number will you end up in if you were the first guest, unfortunate guest, in the first room before this process started? You will never get a room, ever. How many see that? So it's worse than taking a long time. You're not even providing rooms for people. That's worse. Even if you took an infinite number, they still won't have rooms. Think about that. Let me ask you another interesting question, even on the first part. Why can't you take this guest and put it in the last room? There is no last room. How many see that? There's no last room. And if there's no last room, there's nothing beyond that last room. And you can't put this guest all the way down at the bottom because there is no end at this long set of rooms. So you can say the words, put the guest in the last room, or put the guest in the room beyond the last room. You can say that, but it doesn't make sense to say that. You're just making noises. It doesn't have semantic meaning to say that. Right? So be careful when you use words. Make sure that the words you're using are meaningful, not just defined, but to get juxtaposed together, they should have a consistent meaning together. There's an old children riddle/joke. You're in this closed room, no windows, no doors, no exits, and you have an apple. How do you escape the room? And an answer is, you take the apple, break it into two halves, put the two halves together, make a hole, and then escape through the hole. So you have a whole apple. So you can say the words, but it doesn't make sense. It's just a semantic play of words, right? It's nonsensical. And a lot of people go through life talking like this. Some of them happen to be politicians, but I digress. People say ridiculous things, and they don't even know what they mean, and that much less other people know what they mean. And the words are just nonsensical, just noises, and they don't mean much. So don't do that. In this course, try really hard to get yourself into a habit of not doing that kind of stuff. All right. So back to the more sophisticated problem here. Infinite number of lines, infinite number of guests in each. They all want rooms. What do you do? Yeah, so this is a method of diagonalization, right? So, exactly. So what you can do is label the guests 1, 2, but you don't go 3 here and 4 here. You go 3 here, 4, 5, and then 6 here. You go across, zigzagging across the rows, labeling them like this: 8 and 9 and 10, right? And then 11, 12, 13, 14, 15, 16, 17. So you're numbering all the guests, and this numbering scheme will hit every guest eventually with some well-defined number. How many can see that? Okay. If you did this if you numbered them 1, 2, 3, 4, 5, right down this first row, you'll never get to the second row. Because you can get to the second row after the end of the first row. Why? Because there is no end to the first row, so you'll never get to the second row. You can say the words, they just don't make sense. Okay? So you have to, but you can still do it, but you have to do it in some zigzagging, so-called dovetailing way. And that's the technique of dovetailing. Very important. And once you do that, having all these rows of infinite number of guests in each one of these infinite number of rows is equivalent to this problem of just having one row, because you number them, and then you can pull this trick from this previous problem and accommodate all these guests here. How many see the solution here? Good. Any questions so far? This is going to get deeper and deeper, and you can sort of see why Georg Cantor, who invented all this stuff, started getting crazy and depressed in his old age, and people, when they heard this, didn't appreciate it at the time. Now we know it's brilliant. Yeah. So the goal is come up with a function that's one-to-one and onto, a one-to-one correspondence, so-called. So if you have 3 cars and 3 drivers, you want to do this. What you don't want to do is this. Okay? Now with finite sets, it's pretty straightforward. With infinite sets, not so much. But if there's a way to do it, to put them to one-to-one correspondence, and every object in this set has a unique equivalent object in the other set, and they're matched one-to-one with nobody going lonely by themselves, that's a one-to-one correspondence, and then the 2 sets are the same magnitude, and if they're infinite, it's the same infinity for both sets, not different infinities, because infinities for which you cannot do this, and we're about to show examples of that, right? And the infinity of the integers is referred to as aleph null, or aleph zero. There's an old party song, aleph null bottles of beer on the wall, take one down, what do you have is still aleph null bottle of beer. It's not 99 bottles of beer and then 98 and then 97. It stays aleph null for the same reason. There's even a funny, amusing video that kind of hits on these concepts called Hotel Infinity. For extra credit, take a look. All right, but more seriously here, are there more integers than natural numbers? So the natural numbers denoted by n is a set of positive integers beginning with 1. 1, 2, 3, not including 0. And they're, of course, a subset of the integers. The integers are labeled as a big Z, like a capital case Z. So the natural numbers are obviously not equal to the integers because natural numbers don't contain the negative numbers, but the integers do. And so you might say, well, there's less natural numbers than integers then because it's a proper subset. One is a proper subset of the other. But Georg Cantor pointed out that that's not the case because here are the integers, 0, 1, 2, 3, 4, 5. And here are the negative integers, minus 1, minus 2, minus 3 in red. So these are all the integers, positive and negative and 0. And you can put them into one-to-one correspondence with the natural numbers only using like infinite hotel kind of trick. Right? Take all the positive ones and intersperse them with the negative ones like this, and then number them consecutively. Right? So here are still all the integers, just rearranged. Doesn't change the set. The set doesn't care about order. It's just what's in the set and what's not in the set. So the same things are in the set here that are here. So it's still the integers unchanged. But now you can order them using natural numbers only. 1, 2, 3, 4, 5, 6. And that's a one-to-one correspondence between the integers and the naturals. So they're the same cardinality, the same size. Right? So when it comes to 3 drivers and 3 cars, it's obvious that you can match them. And if you only had 2 cars and 3 drivers, it's obvious that you cannot match them. And one way to show it is you can count the cars, 2, count the drivers, 3, and 2 is not equal to 3, so the 2 sets don't have the same magnitude or cardinality. That's obvious for finite sets. For infinite sets, you cannot count, because it's all infinite. Right? Infinity is not an integer. You cannot count it. So you cannot compare infinities by counting and comparing the counts like you can cars and drivers for finite sets. You have to look for a one-to-one correspondence or show that none exist, and the latter is harder to do. Okay? So this shows the one-to-one correspondence between the natural numbers and the integers, even though one is a strict subset, proper subset of the other. What about rational numbers? Are there more rationals than natural numbers? Between any 2 consecutive natural numbers, there's a lot of rationals, right? Between 5 and 6, there's 5 1/2, 5 1/4, 5 3/8, and so on. An infinite number of rational numbers between any consecutive pair of natural numbers. But it turns out they're the same cardinality, nevertheless. And Georg Cantor showed that. He did it as follows. He basically said, take all the natural numbers here, natural numbers there, and present all the rationals in the plane as the y divided by the x. So the y's are the reds and the x's are the blues. So here are all the rational numbers. And let's leave the negatives alone for a second. So these are all the positive rational numbers. How many agree that every rational number is somewhere represented here as a ratio of the fraction? All of them. Okay, good, because it's true. Now, how do you put that into one-to-one correspondence with the natural numbers? 1, 2, 3. In other words, we're going to number all the rational numbers, even though there's an infinite number of rational numbers between any 2 consecutive integers, which is a strange thing to be able to do. But we're going to use dovetailing again, just like the infinite hotel. Right? We're going to dovetail through all these values in this fashion, and there's lots of other ways to do it. There's also lots of ways that won't work, and we'll talk about that in a second. Once you do this, you just number them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, in order of the green tour. Now you've numbered all the rational numbers with integers, with naturals, which means nobody goes unpaired. All the natural numbers are there in green. All the rationals are there in blue-red. None are duplicated, and they're matched exactly one-to-one, pairwise, which means the cardinalities of these 2 sets is the same, even though they're both infinite, and it seems like there's more rationals than naturals, but there aren't, because we can pair them. How many get this? Questions? This is, it's not long, but it's deep here. Now, what if you said, well, 2 over 2 is really the same as 3 over 3. 2 over 2 is 1, 3 over 3 is... So really 4 over 4 and 3 over 3 is 2 over 2. These are all 1, and many other values are duplicated here in terms of their value. How many see that's going on here? Yeah. What if you try to avoid duplications of values like that? What can you do? Just skip the ones that you already visited. So what you can do is then visit these things without the duplicate. So when you hit 2 over 2, it's the same as 1 over 1. You've been to 1 over 1, so skip this, and this next one will become the third one, right, instead of this one. So just eliminate the ones that you've seen before in terms of value, because they're the same number just represented differently. It's a different representation of the same value. Just skip them. And that still works. How many get this modification? Okay, any questions about this? Okay, and you just keep going. So that shows you that there's the same cardinality for the naturals as the rationals, which is bizarre, because the naturals are a very small, tiny subset of the rationals. Right? Rationals are very, very dense. Between any two natural numbers, how many rationals are there? 5, 10, a Googleplex, trillion? Infinite. How many natural numbers are between one natural number and another natural number? Only a finite number. And if they're consecutive, there are no naturals in between. So how can they be the same cardinality? This apparently very large set of fractions and very relatively small subset of it that's the whole numbers. Well, this is how. And you can also diagonalize or dovetail in this fashion. You don't have to kind of, there's many ways to do it. Will this work, dovetailing in this fashion? How many say it will work also? Yeah. But what if I try to dovetail some other way, like I pick them all up like this, 1, 2, 3, 4, and then hope to pick up the rest? What's wrong with this attempted dovetailing that fails? Why does it fail? Yeah, you never get off row 1, and so you'll never get to row 2, so you haven't established a one-to-one correspondence. But just because you haven't succeeded in establishing a one-to-one correspondence doesn't mean it doesn't exist, because some other way will succeed. So to show non-existence is much harder than to show existence. Right? You can't do it with a counterexample or say, I tried and failed. That's not sufficient. Right? And we'll talk more about that separately. It's like trying to prove that you're a millionaire versus you're not a millionaire. If you want to prove you're a millionaire, it's easy. Show me the money, and I'll know you're a millionaire. If you try to prove that you're not a millionaire, can you not show the money and that's your proof? No, because your money can be hidden or be offshore or in some other real estate or in Bitcoin for that matter. Who knows, right? So one is not the same as the other. All right, so next time we'll keep talking about cardinalities and infinities. This pertains to homework number 1. And keep going on the weekly readings. Please don't be late on that. Can't stress that enough. The TA schedule is on the web every single day of the week, including weekends. There's TA sessions. And the weekly problem-solving sessions will begin this Saturday. They'll be every Saturday at noon. See you around.
didn't do the same with this one. And I was when I bring on doing this one.
Well, that's okay.
Oh, okay. I thought it was yesterday.
I was hoping.
Okay, yeah, I already read it. I just didn't do it. Yeah. And you're talking about I already went through and it's time to do induction. So you much like you prefer
So you prefer not to use induction?